Okay, if you consider a source, okay, if you consider a source, that source has a specific impedance that is referred as Zg. Okay, generator impedance. Okay, now this generator is connected to a transmission line. This is the transmission line. So the transmission line characteristic equation is Z load. Okay, and here there is a load. There is a load. So you have connected to the load. Okay, so as I told you, this can be a signal generator, this can be a coaxial cable, this can be antenna, or this can be a power amplifier, this can be a transmission line, this can be a antenna, or this can be a modulator, this can be a transmission line, and this can be a power amplifier, anything. Okay, so this is okay for anything. Okay, now if this signal, if this is the source, okay, this is the source, this is the source, okay, this is normally referred as source, this is transmission line, okay, this is load. Okay, now you can see that these are the connection point, these are the connection point. Okay, so if this Zg is not matched with Z naught, there is a reflection. Okay, and if this Z not matched with ZL, there is a reflection. Okay, and if you consider this overall circuit, and if you consider this overall circuit, okay, overall circuit, okay, okay, the input of this overall circuit, that is the input here. So that is Z in. Okay, so Z in can be calculated using the Smith chart to transmission line impedance equation. Okay, and if you consider this total circuit, okay, if a signal is fed here, there is a reflection. No, there is a reflection. Okay. Okay. If you consider this total circuits, this is called as total reflection. So, okay. Now here you are considering Zg and only this transmission line. Zg and Z node. But here you are considering for total reflection coefficients, you are considering the overall input impedance. Zd. අන්තිමල් තේරෙනවද කියන එක? Can you understand what I am telling? Not superposition, okay? Actually, it is not, you can't get it just by adding, okay? There is a relation, okay? So try to get that relation if you need, okay? But actually, I am not interested about the relation, okay? What I want you to get the idea, okay? So this is the total reflection coefficients because you have complete this total circuit, okay? And here you have considered only the generator and transmission line. So let's say that that is tau S. Here you have considered transmission line and the load, that is tau A. These are called partial reflection coefficients. This is total. Why this is called partial? Because you have considered only the part of the circuit, Zg and Z naught. Here also Z naught and Zg. But here you have considered all the circuit with this one. Okay. So here that is total reflection coefficients. These are partial reflection coefficients. Okay. So tau S can be rewrite. Okay. So this impedance is Z naught. This impedance is Zg. Okay. So reflection is in this way. So you have to start with here. I told you, no? So that is Z naught minus Zg divided by Z naught plus Zg. Okay. As well as you can write tau L. So how you can, what is the value for tau L? So this is Z del and this is Z naught. Okay, so you have to write the reflection coefficients here. That is tau L. This is tau S. Z G, no, here this is Z naught and Z del. You are going to find the reflection coefficients here. So what is this? Yes. Very good. ZL minus Z naught divided by ZL plus Z naught. Okay. Now you need to find the total reflection coefficients. How it come? Total reflection coefficients means you have to consider all these circuits. That circuit input and input impedance is Z in. Okay. Then how you can find this total? Yes. So how you write? So you have to write the reflection here. You have to write the reflection here. You have to write this reflection. This reflection. Okay. So here the input impedance is the input impedance. That is Z in. Okay. So you can calculate this Z in. If you know this Z del, and if you know the Z naught, and if you know this transmission line length, you can calculate this Z in. Using the Smith chart to using the impedance equation, transmission line impedance equation. Okay, then what is Z total? How it coming? How this term? Okay, yes, you correct, but we are considering this side, this side, this side. From here to here. Then how you it can write? Here we are considering from here to here. So Z del minus Z naught. Yes, correct. Okay. So that will be Z in minus ZG divided by Z in plus ZG. Okay. So you should know these things also. Okay. So this also you have to calculate. You cannot calculate, you have to see. Okay. So these are very practical things from the model. Okay. These are very practical things. Okay. So these are very important when we are analyzing or designing a microwave circuits. Okay. Okay. Now I'm going to, okay. So now I want to, okay, generator and load mismatch. Actually, we are talking about this, no? We are talking about this, okay? We have a generator, okay? We have a generator and we have a load and transmission line is also there. And these are not matched, okay? So there are some reflections, okay? There are some reflections, okay? So we basically, if you consider this one, we will have two partial reflection and one overall reflection, okay? Now, okay. So we have, this is the transient impedance line equation, okay. So you can write, okay. So you can see this, now you can understand, okay. So, so exact scenario, they here also discuss, okay. So this is ZG, and this is so this is source generator impedance. This is load impedance, and this is Z naught transmission line, and this uh, beta is also related with the transmission line. Okay, okay, and here the transmission line length, that is L. Okay, so that is also given. Okay, so this is the reflection coefficients looking into the generator. That means looking into generator means this side. This side. They are talking about this side, looking into the generator. Generator දිහා බලනවා. මෙයාගේ නම් මෙයාගේ දිහා බලන විදිහට. එතකොට reflection coefficients එක එහෙනම් මේ කියන්නේ මේ පැත්තට එක. හරි? මෙයාගේ ඉඳන් මෙයාට යනකොට. From here to here. Okay. So reflection happen like this, in this way. Reflection is happening here, no? If you look into the generator. Okay, now you are considering. So normally generator will emit the signal in this direction, but in this scenario, we are considering the signal is going from transmission line to this side, in this side. Okay, so reflection is happening in this direction. Okay. So this is ZG and this is Z naught. Okay, so that reflection, okay, looking into the generator, that is ZG minus Z naught. Okay, but here we are considering this side reflection coefficients. Okay, this side reflection coefficients. So it will be Z naught minus ZG. Okay, don't get confused. All are same. Okay, all are same. Okay? So here the direction is they consider the other direction. Okay, like this. Okay? Now there is another one. The power delivered to the load. Power delivered to the load. Okay. So power delivered to the load means, okay. So this generator is giving the signal. Okay. So that voltage is V in, the current is I in. Current is considered as I in, V in and I in. Okay. Then, so amount of this feed-in power will be go to the load. Okay. Will be go to the load. Some portion of this feed-in power will be going to the load, okay? And there are some reflection. So part of the feed-in signal will be delivered to the load, okay? So that power is calculated as, okay, V in I in conjugate real part of V in and I, okay? So you no need to, you need to keep remember these things, okay? But you have to get the idea only, okay? So this equation is not much important, okay? So you no need to consider very much, okay? So because here half means you are considering the what is called the average power, okay? So yes, okay. So real part, RE means the real part, okay? So you are considering the average power, so that is half, okay? And so this V in, so you know that power also you can write as VI, okay? Then using V equal IR, you can write V square divided by R. This is the power, okay? So in this way, it is written like this, okay? In varga, in square, V in square divided by Z in, okay? So this is, here it get the magnitude of the power, So it will be the real part, okay? And here Z in, okay? Z in means the load, sorry, the input impedance. So you have to get the real part, okay? Because you are considering the real power, okay? Real power, that is the actual power, okay? So imaginary power you can ignore, okay? So you are considering about the real power, okay? So you can get uh, a equation for the power like this, okay? So this is also you no need to keep remember, okay? Uh, but just have the idea. This is the power. This is the power which delivered to the load, okay? So you can see that that is mainly depending on the real part of the uh, input impedance and real part of the uh, generator, okay? Okay. And uh, also this is the imaginary part. So it is also depend on the imaginary part also, okay? That is imagine on the imaginary part also. X in and xg, okay? So this is the uh, input reactance. This is the generator reactance, okay? So the input here actually input Z in is considered as R in plus J X in, okay? This is that one. And ZG is considered as RG plus JXG. Okay. So RG here, XG here. RG and XG here. There. Okay. Okay. So this is the delivered power. Okay. Just have the idea. You no need to keep remember these things. Okay. You no need to keep remember these things. Okay. Now, now they have considered three steps, uh, three cases, okay, three cases and calculate the delivered power, okay. So in this case, okay, now there is a generator, this is the generator, and there is a load, okay. In this case, what it has matched? This load, here you have the load, ZL. ZL is matched to this transmission line. ZL is matched to this transmission line. Okay, that means ZL and transmission line Z naught is same. Z naught is equal to ZL. Okay, so that is the matching. Okay, so we have talked about the matching. Okay, so if you consider this one, okay, if you consider this one, okay, so you can see that if ZL is equal to Z naught, okay, in this case, if Z naught is equal to ZL, what happened to tau L? If this ZL is Z naught, what happened to tau L? Yes, that will be 0. That means no reflection. That means all the power coming here will be there. Okay? Because these impedance are matched. Okay, so there is no any reflection. All the power coming here will be delivered to the load. Okay, all the power coming from this point will be delivered to the load. If you match this load to the transmission line, okay. So that means you need to construct the transmission line. You need to construct the transmission line equal to uh, transmission line characteristic impedance equal to ZL. Okay. So by varying this transmission line parameters, the length and width of this transmission line parameter, you can do this. Okay. We will talk them later. Okay. How we can change the characteristic impedance of this transmission line. Okay. So using any techniques by changing the width or length, most probably width. Okay. Actually, width is related with the characteristic impedance. Okay. So by changing the width of the transmission line, you can you can you can make the transmission line characteristic impedance to the load impedance. Okay. So that is referred as load matched to the line. That is okay. No? This load is matched to this line. Very simple. Okay. Okay, Randima. Don't get confused. Okay. So that is very simple. Simple case they have considered. This load is matched to this line. Okay. This load is matched to this line. Very simple thing. Then what happened? Okay. What happened? Then the power delivered to the load will be this one. Power delivered to the load will be this one. Okay. So, okay. Now tell me, uh, calculate this one. Okay. Let's say that this is the characteristic impedance of the load of the transmission line, and this is the load impedance ZD. Okay. So you can calculate this Z in using the uh, using the transmission line using the transmission line impedance equation. Okay. So tell me what happened if this Z naught is equal to ZL. What is the value of ZD? If this Z naught is equal to ZL, what is the Z in value? Please tell me. Quickly calculate and tell me, Randima. So, just take the transmission line impedance equation. Then you have to equate this Z naught and ZD. Then check what is the Z in value. What is the input in, what is this impedance? This is the Z in. Okay. In this point, okay. So you are going to calculate the impedance of this point. That is Z in. What is that? Not zero. Check. It is not zero. It is not zero. Just check. Very simple. Z naught is equal to ZL. If Z naught is equal to ZL, what is the ZD? Yes, very good. Okay. So that is Z naught. Okay. That is actually the line impedance. Okay. Because you know that Z in is equal to Z naught into ZL plus J Z naught tan theta tan beta L divided by Z naught plus J ZL tan beta L. Okay. So what happened? This Z L and Z naught is equal. Okay. So here also Z naught J Z naught tan beta L. Here also Z naught J tan beta L. Then this one and this one cancel. So Z in will be equal to Z naught. Okay. So Z in is equal to Z naught. Okay. Z in is equal to Z naught. Okay. Okay. Then, okay, then uh, you will get this much of power that is delivered to the sorry, sorry. This is not the case. Okay, we are considering this one. This one. Okay, we are considering this one. Okay, we are considering this one. Okay, so now this R in and X in is equal to because Z in is equal to R in plus JX in. Okay, then Z in is equal to Z naught. Okay, so okay, this R in will be equal to Z naught. Okay, R in will be equal to Z naught, and the Z naught is always real value. We have taught this. Okay, for the lossless line, we consider this Z naught as a real value. Okay, so there is no imaginary part. If there is an imaginary part, it is a loss line. Okay, for a lossless line, Z naught is always a real value. Okay, so this X in will be 0. R in will be equal to Z naught, and this X in will be 0. Okay, so you will get this equation. From this one, you can get this equation. So this is the power. Okay. And again, there is another one. So here we have considered ZL, no? We have considered considered only this matching. We have considered only this matching. This point matching. No? May match line to load. This matching. We are considering only this matching. So tau L will be 0. Tau L will be 0, no problem. Okay. But there is a reflection here, no? There is a reflection here. Okay. So still there is a reflection. Okay. Still there is a reflection. Okay. So we can't say that by matching load to the line, we can't stop all the reflection, no? Because here still reflections are there. Still reflections are there. Okay. Now what they are going? They are going to match generator to the load line. That means they are going to match this generator to the load line. Okay. At that time, what they are going to do? At that time, what they are going to do? Here, what they are going to do? Now they are going to match the generator to the line. Then what they are going to be equate. Yes, reduce the reflection, but what impedance they are going to equate? What impedance to be equate? Now they are going to match generator to line. Generator is ZG, line impedance is Z naught. Okay. Now what they are going to? Yes, they are going to match ZG to Z naught. That means they are going to map ZG, Z naught. Okay. Then what happened? This tau S will be 0. This tau S will be 0. But there is still reflection here, no? Because line is not matched to the load. Okay? Line is not matched to the load. So there is still reflection. There is a reflection. Still there is a reflection. Okay. There is a reflection. Still there is a reflection. So here also that is not okay. In this scenario is also not okay because it has a reflection. Okay. So there is a reflection. Okay. And here also there is a reflection because here this partial reflection is cancelled out, but there is a reflection. So that reflection is there. Okay. So if you consider this total circuit, there is a reflection. Okay. There is a reflection. So not all the power delivered to the load again. Okay. So here also, if you match Z in to Z naught, sorry, they are going to match the loaded line, okay? Not the line. They are going to match the loaded line. They are going to match the loaded line. Loaded line means together with the load, okay? Loaded line means together with the load. Okay, that means they are going to match this Z in with respect to Z naught. Okay, so here there is no reflection. Here there is no reflection. Total reflection will be cancelled. But still, this line is not matched to this Z naught. So there is a reflection. Okay, still there is a reflection. Okay, maybe it is, yeah, here you can see that. Okay, okay. So tau L may not be zero. So will not be zero. Okay, that means at the load, still there is a reflection. So by matching this Zn to Zg, you can't stop the reflection. It's still not total power delivered to the load. It's still not total power delivered to the load. Okay. So that is here you have another value. Okay. So here, what you are going. Okay. This R in is equal to Rg, this R in is equal to Rg, because you are going to map this Z into generator. So R in will be equal to Rg, X in will be equal to Xg. Okay. So here you can apply, you can substitute Rg. Instead of X in, you can substitute Xg. Okay. So this equation you can get. Okay. So 2 Rg square, that is 4. 2xg square, that is again 4. Okay, so you can get this 4 out. Okay, so you will have Rg square, xg square. Okay, so you no need to remember this equation, but you can see how it became, how this equation derived. Okay, so here simply R in is equal to Rg, X in is simply equal to Xg. Why? You are going to match Z in loaded line impedance into the generator Zg. Okay. So R in is equal to Rg, X in is will be equal to Xg. Okay. And the conjugate, so here also there is a reflection. Okay. And now we are considering conjugate. Conjugate matching means, okay, we are matching the load source. Here you have the source generator. Okay. And there is a loaded line. Okay. There is a loaded line. And there is a Z in. Okay. Here also you have a Z in, input impedance. Okay. Now you are not going to map this Zg to Z in. You are going to map Zg to Z in conjugate. Okay. Zg is going to equal to Z in conjugate. Okay. So that is we referred as conjugate matching. This is very important. Okay. So what is you are going to do? You are going to, let's say that Zg is Rg plus jxg. Okay. So Z in is R in plus j x in. Okay. Now you are going to map the conjugate of Z. Conjugate of Z in means R in minus jx. Okay. So in this case, R in is equal to Rg and Xg is equal to what? Minus Xc. minus XC. Okay, so you are going to map like this. Okay, so that is referred as conjugate matching. Okay, so if the conjugate matching is there, yeah, now I am going to explain it. Okay, so here explain. Okay, so conjugate mapping is there actually. Okay, okay, actually this is the loaded power. Okay, this is the loaded power. This is the this is the this is the load power. The power delivered to the load. Okay, power delivered to the load. You need to maximize this P. You need to maximize the power delivered to the load. Okay, so how can you remember how we can find the maximum and minimum? Okay, so you need to get the derivation and you need should be equal to the zero. Okay, then you can get maxima and minima. Okay, maxima and minima you can get. Okay, so here the same thing is done. Okay, they get the differential. Okay, to maximize me. Okay, they differentiate it and equal to zero. Then they get like this. Okay, okay, they get like this. R in is equal to Rj, X in is equal to minus Xt. At this time, they can get the maximum power transfer. Maximum power transfer. Okay, okay. So at the conjugate mapping, okay, at the conjugate mapping, that means, okay, Z in is equal to the conjugate of Zg or otherwise, okay, Zg is equal to the conjugate of Z in, okay. So that is, we consider, we normally refer as conjugate matching, okay. Uh, so at the conjugate matching, there is a maximum power transfer. Okay, maximum power transfer. Okay, so this is called maximum power transfer scenario. Okay, so you need to have the conjugate mapping. Okay, so why we need conjugate mapping? At that time, we will have the maximum power transfer. Okay, that is the purpose of having conjugate matching. Okay, if you match other way, load to the line, okay, uh, loaded line to generator. So you will not get the maximum power transfer scenario. At the conjugate matching, you will get the power transfer scenario. Okay. So this is, you need to understand these things. Okay. These things you need to understand, but you no need to, you need to, uh, you need to remember this equation. You no need to remember this equation. Okay. But you have to get the idea at the conjugate matching, you have the maximum power transfer scenario. Okay. So that is what, that is the things you should understand. Okay. So at the conjugate mapping, you can get the maximum power transfer scenario. Okay. So that thing you need to understand. So there can be other matching, but at that matching, so those are not uh, uh, optimal solution. This is the optimal solution actually, conjugate matching. Okay, to reduce the reflection, Actually here, the overall reflection will be very low. Okay, uh, in this case, you are going to zero one, you are going to make one reflection zero, but other reflection has a high value. So that is not optimum value. Okay. But here in the conjugate matching, you have the both reflection. Okay. Because at the generator also there is a reflection, at the load door there is a reflection. Okay. But this reflection will be very low and the total reflection also will be low. Okay. If you zero this reflection will be high and the total reflection will be also high. Okay. So that is the case. Okay. So at the conjugate matching, that reflection will be very low. So that is what you need to finally understand. Okay. So you need to know these things. Okay. So this actually you no need to keep remember. Okay. So you can get this equation. Okay. So at the conjugate matching, at the conjugate matching, okay, at the conjugate matching, that means Z in is equal to Zg conjugate. So you will have the maximum power transfer scenario. Okay, maximum power transfer scenario. Okay, so at the conjugate matching, if I ask you to calculate tau total, what is that? Okay, okay. So if Zg is Rg plus jxg. Okay. So I ask you to calculate the total at the conjugate matrix. So what is this value? Please tell me. Not zero. Conjugate matrix, total will not be zero. That is very important. Okay. Total will not be zero. Minimum means not zero. Okay. In this kind of scenario, you can't make zero. Okay. You can't make zero. You can't make a zero reflection. Okay. So there is a reflection. You can't make reflection zero. Okay. Okay, let's see. Okay. So what is total? Okay. Total will be if you in this scenario, right? In this scenario, generator match to the loaded line, then the overall tau will be zero. But there is a reflection at the load. Okay. So the load reflection is there. This load reflection is very high. So no all the power transferred to the load. Okay. So that is what you understand. But at the conjugate mapping, there is a small reflection at the load than at the source. The total reflection also there, but the overall power transferred to the load is high compared to other situation. Okay. So that is what you need to understand. Okay. So here, so at the conjugate mapping means, so Zg is equal to Rj plus Jx Zg, then Zin should be equal to Zg conjugate, that is Rg minus Jxg. Okay. So Zin will be Rg minus Jxg minus Zg. Minus Zg means minus Rg minus Jxg divided by Zin. Again, Rg minus Jxg plus Zg plus Zg means Rg plus Jxg. Okay. So here Jxg cancel out. So you have 2Rg here. Here Rg cancel out. So you will have here minus Jxg divided by Rg. This is the total reflection. This is the total reflection. So reflection is there, but still the maximum power will be delivered to the load. Okay. Maximum power will be delivered to the load. Okay? So this scenario is very important because when we are designing amplifiers, oscillators, you have to consider this conjugate mapping. Okay. You have to consider this conjugate mapping scenario. So that is why I told. Okay. So do you have any problem related with this? Animal, do you have any problem related with this? Okay, so what you need to understand, we can get maximum power at the conjugate mapping. The, at the conjugate mapping, we can get the maximum power. Okay, otherwise we can't get the maximum power to the left. Okay, so maximum power transfer scenario, maximum power maximum power delivered to load happen at conjugate mapping. Okay, conjugate mapping. In the conjugate mapping, we can get the maximum power. Okay, so this is a theory actually. Okay, we have proved this by getting the differentiation and find the maximum point. We prove this. Okay, so you no need to familiar with the proof. Okay, but you can just have idea. Okay, that may be good for your mathematical knowledge. Okay, but this one you should understand. You should keep in remember. Okay, okay. Now tell me. Now tell me. Let's say that you have a source. You have a source. Let's say that it is 50 ohm. Your source is 50 ohm. Okay. And you have a transmission line. You have a transmission line. And you have the load. Let's say that load is 75 ohm. 75 ohm. Okay. So 50 ohm, 75 ohm. Okay. Okay. So to have the maximum power transfer, maximum power transfer, maximum power transfer, transfer to have the maximum power transfer. Okay. What we need to do? Okay. So you need to calculate this Z in. Okay. Using this loaded line and maybe the transmission line length may be there. So you can calculate the Z in. Okay. 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 So there is a Z in. Okay. There is a Z in value. Okay. Okay. Now what you need to calculate, what you need to do to have the maximum power transfer, you need to get Z in is equal to Zg conjugate. That is the conjugate machine, no? So what is the conjugate of Zg? 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 If Zg is 50 ohm, what is the conjugate of Zg? Okay, conjugate of Zg also will be, conjugate of Zg also will be 50 ohm, no? 50 ohm, because there is no imaginary part. Okay, so for the real value, conjugate also will be the real value, no? If you consider 50, the conjugate of 50 is 50. Okay, if there is an imaginary part, j 25 or something, then conjugate will be 50 minus j 25. But minus J0 means again 50. Okay. So you will have the 50 here. Okay. So what you need to do? You need to have this Z in, which is equal to this 50 ohm. Okay. If these loads are real value, if this is a G and this load are real value, this Z in should be equal to the generator value to 50. Okay. Then if you consider, okay, okay. So if you consider, for example, let's say that you want to calculate the characteristic impedance of Z0, characteristic impedance of Z. This what is this transmission line? How we can calculate this Z? Okay, so you can easily calculate it. Z in, that should be equal to 50 ohm, is equal to Z naught. That is what you need to calculate. Z naught, okay, 1 plus, sorry, ZL, that is 75 plus Z naught, now if I go that way, it is somewhat difficult to solve. Okay, so I will tell like this. Okay, you need to equal the input impedance of this loaded line to 50. Okay, you need to select the input of the loaded line to 50. Okay, so Z in should be 50. Okay, okay, and here you have another load. Okay, let's say that is RL. Okay, so this is load RL. Okay, and here 50 ohm is RS. Okay, let's say that characteristic impedance is Z0. Okay, so what you need to do? You need to get the input impedance Z in, that is equal to RS. Again, that is equal to Z naught RL plus J Z naught tan beta L divided by Z naught plus RL JRL tan beta L. Okay. So this is the transmission line impedance. Okay. So you are now we are considering. Okay, I will take this. Okay, I will keep this. Maybe you will get confused. Okay, so I will keep this value later. I will get this value later. Okay, now I am getting some real value, real impedance. Okay, real impedance value. Okay, Rantimal, maybe you have disconnected. Okay, now you can just think from beginning. Okay, so you have a source. Let's say that you have a source. Okay, the impedance of the source is RS. That is a real. That is a real value. But previously we have considered complex values. Okay, complex value. The ZS or ZG is equal to RG plus JXG, like this. Okay, so now you are considering only the real value RG. Okay, so XG is equal to 0. So you have a real impedance source. Okay, and you have a transmission line. Let's say that transmission line impedance is Z0. Okay, and you have a load here. You have a load here. Okay, the load is RL. That is also real. ZL is equal to RL plus JXL. No? Now JXL is 0. So ZL is equal to RL. Okay. So you know that at the conjugate mapping, we can get the maximum power transfer. Okay. So here also, if you consider the conjugate mapping, what you need to do, your Zin, this input impedance, Zin should be equal to conjugate of Zg. The conjugate of Zg is Rg minus Jxg, but this Jxg is 0. So again, it will be equal to Rg. Okay. So conjugate of the real value is the same value. Okay. So that is what you understand. Okay. 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 Now you need to equal this Z in to Rg. Okay. You need to equal this Z into Rg. Okay. So so that is the conjugate matrix. So if I get the transmission impedance, line impedance, Z in is equal to Z naught, ZL plus Z naught tan beta L, okay, tan beta L divided by Z naught plus ZL tan beta L. This is J and this is also J. Okay. So this is the transimpedance line equation. Okay. Now Z in, what is the Z in? Z in should be Rg. You need to find the Z naught. Okay. ZL is RL. J Z naught tan beta L. Z naught J ZL tan beta L. Okay. So actually here you can solve. You can find the value for Z naught using this Rg, RL, and tan beta. You can find the value. Okay. You can find the value. Okay. Now I am going to select this beta L as pi by 2. This beta L as pi by 2. What's that means? Okay, what's that means? If this beta L is pi by 2 means what's that means? Okay, so you know that we have, yes, okay, it will be infinity. Okay. This is RL, okay, this is RL, okay. Z del, no? Z del is equal to RL, okay, because we are considering real value, okay. Okay, so this beta L pi by 2 means what? Okay, so we know that, okay, we know that if uh, if a wave is going lambda, that means lambda means the wavelength, okay, length, the uh, corresponding angle is 2 phi. Okay, so this is centimeter, this is meter, this is radian. So when a signal traveling lambda meter distance, okay, corresponding uh, angle will be 2 phi. Okay, this is normally referred as electrical length. This is normally referred as electrical length. Okay, so for a unit lambda, for a unit distance, it will be 2 phi divided by lambda. Actually, this is referred as beta, no? This is referred as beta, phase constant. Okay, this is defined as beta, 2 phi by lambda. Okay. Uh, so if it is L, if it is L distance, okay, so this will be 2 pi by lambda L. Okay, this is actually B type. This is actually B type. Okay, to have to have if the beta L equal to 5 by 2, to have beta L is equal to 5 by 2, what is the L will be? L will be lambda by 4, no? Yes, very good. Okay, L will be lambda by 4. Okay, so if L is lambda by 4, if L is lambda by 4, okay, beta L is nothing but 2 5 lambda is into L. So L is lambda by 4, that means 2 5 by lambda by 4. So lambda lambda cancel out, you can get 2 5 by 4, that is 5 by 2. Okay, so if you get L is equal to lambda by 4, L is equal to lambda by 4, okay, okay, then beta L will be 5 by 2. Beta L will be 5 by 2. Then this tan 5 by 2 means that is infinity. Okay. So if you get this tan beta L out of this equation, okay, so you can write like this. Rg is equal to Z naught tan sorry, you need to divide all these, okay, you need to divide all these term by tan beta L. If you divide all these term by tan beta L, you will have Rg is equal to Z naught, okay, so RL divided by tan beta L plus J Z naught, because tan beta L cancel. Okay, so here also Z naught tan beta L plus you will have J RL. So you will have this. Okay, so if beta L is equal, if you consider L, if you get L as 5 by 4, okay, this is we called quarter length. Okay, we get the quarter of the wavelength, so that is called as quarter length. Okay, quarter length. Okay, if you select the quarter length, okay, so tan beta L will be infinity, so one some value divided by infinity, it will be 0. Some value divided by infinity, it will be 0. Okay, then you will have Rg is equal to, here Z naught into, see, this J and J also cancel, then Z naught is square divided by RL. Okay, then you can calculate this Z naught as Rg RL. Okay, so Z naught can be easily calculated as RGRL. Okay, so what I want to tell you is that if you have, this is very important. Okay, if you have a source and it is a real with the real impedance value, and also you have a source load with the real value, okay, with the real value, for the conjugate matching, for the conjugate matching, you need to equal, conjugate matching is the maximum transfer value. Okay, conjugate matching is the maximum power transfer value at the conjugate. Okay, conjugate, you need to equal this Z in conjugate of Rg. That means Z in should be equal to Rg. Okay, this Z in you can equal to Rg. Okay, Z in should be equal to Rg. Okay, so you can find the characteristic of this transmission line, okay, Z naught easily if you get quarter wavelength. If you get the quarter wavelength of this transmission line, that is lambda by 4 wavelength, okay, quarter length, okay, quarter length, you can easily find the corresponding Z naught. So that will be square root RGR. So this is at the conjugate mapping, no? This is at the conjugate mapping, okay? So conjugate mapping for a real source and uh, real impedance, okay? For the real load and for the real load impedance and real source impedance, okay? You can do the conjugate mapping easily, okay, by getting the lambda by 4 length transmission line, okay, uh, with respect to lambda by 4 transmission line section, and you can easily calculate the Z value, okay. What you have to do is you have to get the square root of RG and R, this one and this one, okay, okay. So that is very important, okay. Yes, okay, lambda by 4, at the lambda by 4, okay, you can easily get, okay. So you have done the matching, no? Okay, now tell me, what is the value of overall reflection in this time? What is the value of overall reflection? So later, so maybe you can remember that overall reflection you have defined as Z in minus ZG, Z in plus ZG. So if uh, if this RL and RG are real value, what is the total value? What is the the reflection value? Now you are going to equate Z in to Zg conjugate, no? So Zg conjugate is equal to Rg. Zg also equal to Rg. So you will have Rg minus Rg plus Rg. So you will have 0. Okay. Yes, very good. Okay. So you can understand that at when the impedance are not real, the load impedance and source impedance are not real, the overall reflection will be 0, because you have to match this input impedance equal to the source impedance. So to the reflection coefficients, total reflection coefficients will be 0. And you can get that value, and you can get the corresponding transmission line characteristic impedance by getting lambda by 4 length, okay. So that is equal to RGR, okay. So what you have basically do, you have basically mapped this RG to RL using the transmission line, no? Using the transmission line, okay. So that transmission line is lambda by 4, that is quarter length, okay, quarter wave, okay. Okay, so this is actually the transformer, okay. So this is the transformer. So you have transformed this RG into RL, okay. You said not plus root and minus root. I can't understand what is that. Oh, yeah. Minus value you don't know, because there is no minus impedance. So the minus impedance are not there. You have to get the, because we don't have minus resistance. No? Minus resistance value we don't have, okay. The resistance value will be a plus value. So you have to consider only the plus value. Okay, that is good. Okay, that question is good. Okay, so you have to consider the plus value. Okay. Okay. So what you have do, you have mapped real source impedance into a real load impedance. Okay, using the transmission line. Okay, so that is we normally referred as impedance impedance transformer. Impedance transformer. Okay, and you have select the lambda by 4. That is normally referred as quarter wave transform. Okay, so this is quarter wave transform. Okay. So quarter wave transformers you can use to map real source and real load impedance. Okay, so there is no reflection. Okay, without no reflection. So, but that is only we can use only for real source and real um, load value. Okay, real source and real load value. So, so you need to so here the quarter wave transformer is there. Okay, yeah. So you can just read this. Okay, and you can get a good idea if you have read this. Okay, if okay, so just read this and try to get the idea. Okay, so this is the quarter wave transformer. You have mapped Z naught to the RL. Okay, so you have find the characteristic impedance of the transmission line. Okay, having the square root. Okay, RL not equal to RG. If the RL is equal to RG, you no need to have a matching. You can directly connect that too. Okay, if the RG is equal to RL, you no need to map. You no need to have a matching. Okay, if this RL is equal to RG, you no need to have a matching because there is no reflection. You can directly connect them without a transform. Okay, here the RG and RL is not equal. So there is a reflection. So you have to consider a matching circuit here. That matching circuit is the quarter wave transform. That is the quarter wave transform. Okay, so that is quarter wave transform. Okay. Okay, so we will stop here. Okay, we will stop here. And uh, BNC cable, there is no such thing called BNC cable. BNC are the connectors. Called BNC. ගහලා බලන්න internet එකේ BNC means I can't remember connector. That is a connector line. So normally coaxial cable has two connectors, BNC connectors and SMA connectors. Okay. Actually, there is other type of connectors. Okay. Can you see me, Pandima? Can you see me? මා පේනවා? Okay, wait a minute, Tori. A minute. Animal, this is the cable, okay? This is a cable. This is a coaxial cable, okay? If you cut this, you can see that there is a inner conductor and outer conductor, okay? So this is a cable and this is the connector. The cable is connected to the connector, okay? So this is a SMA connector, okay? So if you consider this one, okay, actually this is amplifier, okay? I'm sorry, this is not amplifier, okay? I have amplifier here. Yeah, this is amplifier, okay? This amplifier, okay? So, so you have to give some power here, okay? Otherwise, this is not working because the amplifiers are normally active, okay? So, if you want to, if you can get a signal here, let's say that this is your generator, then you can get a signal from the generator, okay? So here also you have SMA female connector and this is a male connector. So you can connect that together. So now signal generator will give the signal, okay? Then you need to feed it to the power amplifier, okay? So here also female connector, then you can connect, okay? So these are SMA connectors, okay? These are SMA connectors, okay? And there is another type of connectors, okay? So this is very small coaxial cable, okay? But maybe you can remember that for our, you can see there, okay? I will show you. Maybe you can see here, okay? This oscilloscope, okay? Here, these are the BNC connector. Okay, these are BNC connectors. Okay, these are BNC connectors. Okay, these are also connected with the coaxial cable. These are BNC connector. This is a male BNC connector. Normally, oscilloscope and signal generator have female. Okay, so you can connect the. Actually, this is in here. You can see. Okay, there is inner conductor and this is the outer conductor. So you have to solder the cable to this connector. Then you can make a coaxial cable with this connector. Okay, so this is a BNC connector. Okay, and this is another type of connector. This is we call DIN connector. Okay, so normally this is we are using for half-inch coaxial cable. That means the diameter of the coaxial cable is half-inch. Okay, so and there is another type N type that is also used for half-inch cable. And 7x8 coaxial cables are there. For that one, we are using 7x8 connector. Okay. So different type of BNC connectors are there. Okay. But in labs, we are mainly using this type of one, SMA connector. Okay. And BNC connector. Okay. I think maybe you are asking why BNC better than SMA or something, no? Is that so? Is that so? I don't know. Anyway, okay. So we can't say that the SMA are better than coaxial BNC. I don't know. Okay. We can't tell like that, I hope. Okay. Uh, but normally BNC SMA connector has actually 50 ohm resistance. Every SMA connector has 50 ohm, but BNC will have 75 and 50 ohm. Okay. And this DIN connector also 75 ohm. These are also 75 ohm. These are also 75 ohm. Okay. This side we have to connect the cable. Okay. Then this is the connector. Okay. This is a female connector. Okay. And the male connector should be there to connect that one. Okay. I have no idea the BNC is better than SMA likewise. Okay. But normally coaxial cable are better than Cat5 cable. Okay. Because coaxial cable bandwidth is high and the distance is also high. We can send a signal more. As I can remember, we can use coaxial cable to send maybe 100 meter. But the Cat5 cable, you can't, maybe 50 meter or something. And also the bandwidth also, I can't I can't remember exactly, okay, but maybe using internet you can find those things. Uh, yeah, thank you for remembering, okay. Uh, okay, running.